Hello. Well, it's going to be hard for me to fit this into the exact parameters that define this session, so I think I'm just not going to try and hopefully proceed through this talk and then maybe get to some boundary issues at the end. So, without further ado, okay, so this is a brief outline of my talk. First of all, I'm going to give an introduction to Yellowstone Volcano and its instrumentation network, a very short tutorial on GPS and how it's used for volcano research and monitoring, some recent GPS observations showing an uplift episode near Norris Geyser Basin, something that we found extremely interesting, and hopefully you will too, how we modeled and interpreted that uplift, and then finally the significance, implications, and conclusions of what we saw in this remarkable year, 2014. Believe it or not, this is a simplified geological map of the Yellowstone area. This purple boundary here defines the most recent of the Yellowstone calderas. It formed about 640,000 years ago. In salmon or pink here are post-caldera volcanic deposits, mostly lava flows. You notice you also have a few post-caldera flows in the so-called Norris Mammoth corridor. Not going to be talking about lava flows today. I'm not going to be talking about volcanic eruptions at all, in fact. The last time Yellowstone erupted was 70,000 years ago. So in no way is Yellowstone due for an eruption. Nonetheless, the remnant magma body still has a lot of heat associated with it, and that heat is driving a lot of very fascinating processes within the park, and these processes give us an opportunity to learn a lot about what's going on beneath the ground. Oops. So this is the current geophysical instrumentation network in Yellowstone National Park. In blue are seismometers. In red are GPS receivers. Not shown, we have a variety of other instruments, tilt meters, strain meters, etc. I'm not going to tell you what each one of these things does. The seismometer, as you might imagine, records earthquake activity. GPS receivers record ground deformation, and I'll get into that in a moment. The density looks pretty impressive. And it is, and we've made great strides in the last 10 years monitoring this volcano, but there's still a whole lot of park. And even though we have a lot of instruments, our instrument density is actually quite a bit less than at other important volcanoes in the United States. Okay, GPS, everybody knows what GPS is. It's a constellation of satellites that lets you get your coordinate at really any place within the constellation, but most of us are focused on the surface of the Earth. How are we going to use that for anything useful scientifically? Well, you know that your handheld at best gives you an accuracy of about 1 meter. With our precision instruments, and yes, they are very expensive, we can get precisions down to about 5 millimeters, sometimes a little better, sometimes a little worse. There's a whole lot of interesting science, and there's a good story behind how we got from here to here, but that's well beyond the scope of this talk, so you'll just have to take my word for it. So we can use this precision because we can detect, well, we can monitor the position of a particular point on the Earth's surface and see it go up, down, left, right, north, south, whatever, and we can monitor these changes as a function of time. So what does GPS measure? Well, I'm not going to go through all of this. I just want to emphasize what I said last. It's the position change we're interested in. We're not really interested in the precise elevation above sea level of the Norris Geyser Basin. Rather, we're interested to see how the Norris Geyser Basin's elevation is changing as a function of time. Here are some GPS instruments deployed in Yellowstone. This one's in Mammoth. It's actually only about a mile from here, a little less. Important thing is the antenna's got to be up in the air. It has to have satellite visibility. This thing here, I don't know what it is. It has nothing to do with USGS. Okay, so as I promised, we're going to talk about deformation near Norris Geyser Basin. I've gotten rid of the seismometers, and now you're looking at the network of continuous GPS receivers. They're recording all the time. Again, I'm going to focus in on the Norris area, and we're going to look specifically at the NRWY GPS receiver. Okay, this is a time series. You often see time series like this for GPS. It's broken into the three components, the vertical, the north, and the east. You've got 2010 here all the way to 2015. What I want to call your attention to is back last year, around August 31st, we noticed a little bit of a deformation transient. Let me see if I can make that clearer. There. So you see that we see a bit of a transient in the vertical and a bit in the north. In other words, this station is moving a little bit south and a little bit up. Compare that to the relatively boring signal before, and we call that a transient. Not an impressive transient, but still something that's detectable. This really caught my attention because of something else that happened right around that time, which was the eruption of Steamboat Geyser for the first time since 2005. Now, as my colleagues are quick to point out, correlation does not equal causation. And in spite of the fact that I was sort of really mesmerized by this coincidence in time, in retrospect, it turned out it probably doesn't have anything to do. That is, the steamboat eruption is completely independent from this other observation. But nonetheless, it motivated me to watch this more closely. Okay, so, I should go back a slide if I can. We're going to advance 2 months in time, and we see, oh, look, your transient, it sort of died out. Not very exciting. You've moved basically as much of a centimeter, and now you seem to be back to business as normal. We kind of lost interest. We still pay attention to the data, of course, because of our due diligence. And then another 2 months went by, and all of a sudden it started doing this. And here we are. We are in now about February 1st, 2014 now, and we've gone up, 3 centimeters at the Norris Geyser Basin, and we also have equivalent signals, well, not exactly equivalent, corresponding signals in the north and east. So something is definitely going on in the Norris region. Okay, so our response to this is we put out an information statement. This isn't a forecast, it isn't a warning, it's an information statement. We put these out routinely if something unusual is going on. The take-home point, ground deformation occur commonly in Yellowstone, pose no direct volcanic hazards, nor do they imply that an eruption is pending. And that's an important point. Sometimes the most important thing we do is tell people when the volcano is not going to erupt. All right, so here we are. We're at the end of January now, and let's go another 2 months forward, and what do we have? Oh, it keeps going. So now this has really gotten our attention. Again, not because we're frightened, but because we're really interested in what's going on here. This is quite different from the previous 4 years, and as you'll see later, previous 10 years. So this was a quandary, a scientific quandary. The public was well aware of this. The forums and the enthusiasts who watch Yellowstone carefully definitely knew what was going on. This came out, and you see, I wish I could get this kind of readership. And this one, of course, was pretty easy to disprove, given that the park exit is actually that way, so they were running into the park. But nonetheless, we laugh at it, but this caused a lot of trouble, and I think my Park Service colleagues will agree that this stuff gets picked up by the mainstream media and social media, and all of a sudden it's sort of fact. All right, so here we are back in the world of science, and we're saying, okay, here we are, it's the end of March, it's been doing this now. Well, if you start from August, well, what is that? I don't know, six months, 7 months? Well, what's going to happen now? Well, one way we can answer that question, let me go back to the slide, is remember we've got 3 components. We've got the vertical, the east, and the north. Let's ignore the vertical, even though it's the most striking signal. And we can plot the horizontal ground deformation as vectors. So essentially Norris, as I said, is moving to the south and then also to the little east. Norris has the biggest signal, but you also see that the signal is creeping out to other nearby stations. Wouldn't it be nice if we could fill in some of these gaps? Well, actually we can, because we can visit benchmarks that are just very small, no permanent infrastructure. We can pop in, get a measurement, pop out, and then that fills it in. So we got 2 additional stations. And these are actually velocities in centimeters per year. So that scale is 25 kilometers map and 5 centimeters a year. So you're talking about 6, 7 centimeters a year. It's bigger than plate tectonic. The plate tectonic signal has been removed. I should have pointed that out. All right, so what does it all mean? 5 minutes. Well, we want to model the data for the source type, for the location, the depth, and strength. We want to infer the geologic significance from the model results. Of course, we have to be mindful of all the assumptions that go into our modeling and their limitations. Consider other relevant data sets that might bear on this: seismic, geochemical, hydrological, etc. And then develop scenarios and assess the relative likelihood. This part 5, we don't really do much in Yellowstone because we haven't had a crisis in, well, recorded history that would really merit this, but at other volcanoes we do. Okay, so you can model this signal. This is kind of a busy slide, forgive me, but the black arrows, the black vectors are the observation, the red is the model prediction. So we do an okay job of fitting the data. The big signal at Norris here is really dominating, but nonetheless we can make some general inferences about what's going on. There's a locus of pressurization near Norris. Its depth is at least 4 kilometers below sea level, and it's probably closer to 8, meaning that this is not going on at the surface. It's not something that is going to pose a surface hazard anytime soon. The strength, well, the delta V, the volume increase is about 20 million cubic meters per year. I realize that number is just contextless. I can say that for volcanic systems, that's a pretty weak number. It's not terribly significant, but it is enough to produce some nice-looking ground deformation, especially if it happens quickly. Our interpretation was pretty simple. We have an accumulation of magmatic gas and fluid beneath an impermeable layer. It's just bulging it up. Conclusion: scientifically interesting, but little concern. Okay, so what happened? Well, there was an earthquake. There was a magnitude 4.8 earthquake. I think some of the park staff and people who live in the area felt this earthquake. It was a 4.8. It was the largest Yellowstone earthquake in 30 years. And that headline there got a lot of media inquiries and prompted a lot of hand-wringing. But really, it's kind of what we expected. Okay, so we were there, and it's like the stock market. This cannot just keep going. And eventually, what we find is that it went down. And it went down really abruptly. And does anyone want to guess where the earthquake occurred when I put it on the time series? Right there. So it's actually qualitatively a pretty simple system. Not that we really understand it. That's why I said qualitatively. But you have a pressurization. It persists for a while. It exceeds some yield strength. An earthquake breaks it. The volume is now able to leave. The pressure goes down. Things sort of return to normal. This is just a zoom in. I'm not going to talk about this in the interest of time. I just wanted to point out that the Norris, this baseline actually goes back many years. So let me jump to the conclusions. Jump to conclusion. So such an abrupt change in deformation trend is unprecedented in Yellowstone, but that's only because we've been looking in this detail for only a decade or two at most. The coincidence between the change in deformation trend, and the 4.8 earthquake implies causality. We can argue about that. It's certainly not a law of nature that has to be so, but it sure fits. The latency between the earthquake and the start of the reversal could be telling. It turns out that the reversal actually occurred about 6 days after the earthquake, which is a little weird. But again, it's probably telling and can inform our further modeling. The reversal requires volume loss. Where did the volume go? Did it go back down? Did it go left? Did it come up? We don't know. We're working on that. And the Norris area and the caldera can deform independently. I didn't really get into this, so it's difficult to evaluate its significance, but it's something that has us pretty excited. And I will conclude from the Yellowstone Volcano Observatory, which is a boundary-crossing partnership among USGS and the National Park and several academic and other scientific agency collaborators. Thank you very much.